Okay, welcome to today's online lecture. What we're going to do to start out is just briefly recap the economic input-output model. We went through all the math at the end of the lecture on Tuesday, and so we'll just kind of start by recapping that, and then again explain how to take this input-output model and turn it into a life cycle assessment tool. There's two reasons that you might be interested in this. One, obviously, the fact that you can use this economic input-output tool to do life cycle assessment is itself interesting. There's a publicly available tool at eiolca.net. And secondly, on the final project, we'll be using the exact same type of mathematics to, instead of study how money flows through the economy, to look at how interdependencies flow through critical infrastructure systems. Turns out to be the exact same math. The only difference is what the letters Xij mean, what OI means, what Fi means, and so on. So we'll pick up on that when we go into more detail about the project. Okay, so the slide I've got here up on slide 22 is just the recap of the table of an economic input-output model. Remember that it starts off by going out and actually collecting data for things like X31. That's the total amount in dollars of output from sector 3 that is input to sector 1. Or in other words, it's what's sold from sector 3 and bought by sector 1. Of course, you can do this for all of the 400 and something plus sectors of the economy, and every year that will give you in like billions of dollars how much cash is flowing from each sector of the economy to each other sector of the economy. We explained that if you look at the total amount of output by a sector, call that Xi. That's, of course, going to be equal to things that you sold to other things in the economy, other sectors of the economy, OI, plus things sold to the final consumer, Fi. So in other words, you can think about this as the total number of cars produced would be equal to the number of cars sold to every other sector of the economy, plus the number of cars sold to end consumers. The way that you can see this is if you sum across these tables here, as we explained in class on Tuesday, the sum across a column tells you how much output went from sector 1 to sector 1, to sector 2, to sector 3, and so on. If you sum that up, that will give you O1, the total amount of money output from sector 1 that was input back to other sectors of the economy, including X11, which is things that were sold from sector 1 to sector 1. Okay, so you can do a row sum to get O1, the intermediate output. The amount that you sold to the end consumer is F1. So things that you sold to other sectors of the economy plus the end consumer gives you the total output. We explained in class that if you, instead of summing across the rows of these tables, if you sum down the rows, this tells you how much output from sector 1 was sold to 1, plus the output from sector 2 sold to 1, plus the output from sector 3 sold to 1, and so on. Well, that tells you basically the value of all the inputs to sector 1. And the value of all the inputs to sector 1 does not equal the total output of sector 1. It's the difference between what the value of the incoming goods are and what the value of the outcoming goods are is the value added by sector 1. So Z1 is the intermediate input. That's the column sum here. You add on the value add, and that will give you the total output X1, which is the exact same total output as this X1 over here. Okay, and so that basically describes how you would, what all the data in this table looks like. The trick in EIO-LCA is to not use this table directly, but instead to convert this into a normalized form where you're really just mapping how many dollars from each sector go to every other sector so you can compute a ratio. Okay, so the slide 23 just defines that intermediate output that we just walked through. I mentioned in class that if you sum down the final demands, that tells you the GDP, and we just walked through the analysis here about how to calculate the value add for each sector. The trick in building the model, though, as I was alluding to, is you take these dollar figures and you actually normalize them. You let Aij just be taking all your Xij terms and dividing them by Xj. In other words, it tells you if this is the total amount of goods that are sold from sector I to sector J, and you divide by sector J, then it really just gives you the total input from sector I needed for each dollar of output from sector J. That coefficient will become the useful piece of our model because it's telling us on a dollar per dollar basis how money flows through the economy. We can, of course, do that for every xij term in the table, and instead we get a matrix A that tells us how those dollars flow. And then I basically build up in class this argument that, well, look, if you have for each row, if you have the intermediate output from a sector I plus the final demand for a sector I, that must be the total output required from that sector. That's what the first equation is. This is a scalar equation. Xi is a number, Oi is a number, Fi is a number. Well, this Oi, by definition, we said it was the row sum. So we can actually just substitute Oi for Xij, right? Summing across the row, summing across the j, Xij will give us exactly back Oi. So that's just a variable change. And then we defined Aij to be nothing more than, Aij was nothing more than Xij divided by Xj. All right, we got that right here. Well, of course, if you multiply through by Xj, so you have Aij times Xj, that's equal to Xij. Well, we can use that as a substitution right back here. We are literally substituting in Xij for Aij Xj instead. So there's nothing tricky going on here, just a variable change by substitution. Okay, but the difference of putting it in this term Aij, what that allows us to do is actually see this term here, which, by the way, is just another way to calculate this scalar value Oi. It allows us to see this as actually summing across the row, or said differently, doing a row, the row of A, the ith row of A times the vector x, times the vector x, which has elements in it xj. We can see that as a row times a column vector, and actually write that then as ai times x. Now here ai is literally the row vector ai1, ai2, ai3, and so on. Okay, and now this x is actually a vector of size n. It has x1, x2, x3, all the way up to xn in it. So read this as a row vector times a column vector, which is equivalent to the expression right here. What's nice about doing that is still we're looking at a scalar equation here. We're only looking at a single number, the total output for sector I, and it's equal to the intermediate output for sector I times the final demand for sector I. But if it's true for every single sector I, we can write down the system of equations that must hold true for the entire economy. In other words, not just sector 1, which we have here, and not just I equal to 2, sector 2's equation, and not I equal 3, sector 3's equation, but we can actually write it down for the entire set of sectors of the economy. So the vector x is now equal to the matrix x times, or the matrix A times the vector x plus the final demand vector f, which has elements in it, f1, f2, f3, all the way up to fn. Okay, so this gives us a system of equations. There's no unknowns in the economic input-output data yet. We have x, which was in dollars of total demand, is equal to, another way of saying it is just the intermediate output of all the sectors plus the final demand of all the sectors. But the trick in the modeling is actually to then recognize that, look, if I, instead of putting in the final demand for the entire economy, F here, if instead I put in a final demand of something I want to analyze out of the economy, like what happens to $10 of spending in a particular sector, or what if I buy a $30,000 car? What does that require in terms of total output of all the sectors of the economy? Well, then F is something that I now choose, and X becomes an unknown. The data A, which we learned or computed by looking at how the economy worked through how dollars flowed through the entire system, that A is still data that we learned from the economic input-output data. But again, now F is specified by us, and we want to find the x that is the total demand. Of course, the trick is that x as an unknown now shows up on both the right-hand side and the left-hand side of the equation, and that's fine. It's still a system of equations with n unknown variables, x1, x2, x3, all the way up to xn, and there are n equations. N unknowns, n equations. Depending on how the system is structured, we may have a solution, we may not have any solutions, we may have a family of solutions. And it turns out that the way that this problem is structured, you can always guarantee that there is a unique solution to this system when you're working with these economic input-output models. Okay, well, how can you solve it? Well, I don't care. Basically, any way that you are comfortable solving a system of equations with n unknowns and n equations will work here. If you want to solve it by hand, you can. Linear algebra just gives you a convenient way to write down what the system solution looks like. And no different than if, for just a moment, if x was a scalar and like a single unknown, and a was a single quantity like the number 2, and f was a single number like the number 1, you could solve x is equal to 1x plus 2. That has a solution. In the same way, the system of equations, you can express that, right? And I walked through this argument that one kind of convenient trick that we do for solving systems of equations and matrices, we actually recognize that the vector x is actually an identity matrix times the vector x itself. The identity matrix, remember, as I explained in class on several occasions, is a matrix that is an n by n matrix with ones only on the diagonal. So boy, this is a bit nuanced. The entries of the matrix I, when the entries are the same, so I11, I22, I33, I44, and so on, those all carry the value 1, and all the off-diagonal terms like I12 take the value 0. So that identity matrix, it's kind of buried in the name, but when you take an identity matrix and multiply by the vector x, you get back exactly the vector x. Okay, what that allows us to do is pull this ax term onto the right-hand side, pull off the x's, both off of the identity matrix and off of the A matrix. And in the case of the scalar, we just like to divide the left-hand side and the right-hand side by the term I minus A. Unfortunately, with a matrix, you can't divide. You have to you have to multiply the left-hand side and the right-hand side by other matrices. In fact, the right matrix to multiply the left-hand side to get rid of this term is I minus A inverse. You multiply it on the left-hand side, and that gets rid of the I minus A term. On the right-hand side, you pick up a term I minus A inverse. And I minus A inverse, you can calculate in Python. And it will return you another matrix of size n by n, and we call that matrix S. At the very end of class, I was explaining that S has a very nice property to it, right? If you take, as we've done in the past, the final demand vector F, and you let it just equal 1, 0, 0, 0, 0, and so on. So it's a very special vector, everything 0 except the first entry. What that does is effectively isolates the very first column of S. Remember, you can view F as these mixing coefficients of the columns of S, and since all the mixing coefficients except the first one are 0, then you're left with just the first column vector of S. What that does, F being $1 of final demand, tells you the total amount of output required to produce that final demand. In other words, the very first column of S is literally how much total demand you need per dollar of final demand of the very first sector. And similarly, the second column of S tells you the total demand needed for $1 of the second sector of the economy. You want a dollar of the second sector, tells you the total amount of output required for every one of the sectors in the economy to make sure that you get that $1 of final demand. So S has a lot of really powerful information in it. It's the full supply chain effects. It's not just the fact that if you need one car, obviously the car company needs to produce a car for you, but in the process they need steel to make that, and the steel didn't get to the factory for free. Somebody had to ship it, and if that was shipped on a car, then obviously in order to deliver you a single car as a final demand, as a final consumer, somebody is going to have to produce slightly more than a car in order to serve all the other needs, all the other inputs to building cars that actually depend on cars themselves, i.e. anything that was shipped. So S has all those supply chain effects already baked into them for you, where the matrix A did not. Matrix A just told you what you needed in terms of intermediate output to produce final demand. Okay, so there's another interpretation that makes it kind of explicit that this solution where the total demand is equal to, or the total output is equal to I minus A inverse times your final demand vector. There's another way to see this that's more inspired by dynamical systems theory that we covered at the beginning. And the art really is to think about this vector x as the total output required for the final demand plus the intermediate output for the first k levels of the supply chain. In other words, k is going to tell us basically how many times we've been on the phone telling people to build more stuff because we don't have enough resources to produce the final demand that we're after. So in other words, let's kind of start the process out, right? If I tell you that I need a final demand of a single car, obviously on the like very first thing that happens on the 0th step, you know you need to produce a car, right? The total output must be on the first round. You need to produce me a car. That's fine. Nobody's made any phone calls in the supply chain yet. You've got one order so far that's for the car. Of course, the first thing that the car company does when they get a demand, I've got to produce a car, is they go call all their suppliers and tell them what they need to produce one car. Well, that first round of phone calls, they say, well, if I need $1 of final demand, I have some intermediate output I have to produce. I know how much input I need in order to produce a final demand. Okay, so this sort of first round of phone calls, I know I need to produce at least one car for the end consumer, but I also know that I might get asked to produce more cars as well as many other things due to the fact that I'm now requesting from other people to give me inputs to my sector to produce this car. Well, of course, everybody there gets on the phone, and if the steel manufacturer also needs to get electricity and other things, they need more input, right? So in the second set of phone calls, you have not only the final demand to the end consumer, the input required to produce that final demand, but the input required to produce the input required to produce the final demand. That's what this next term does. Well, you can keep playing this game, right? You have the final demand you need to produce. There's all the output you need to produce the final demand, but unfortunately, that term requires that you produce even more to fulfill it. Well, how much more do you need to fulfill it? Well, multiply it by another A. So your final demand times the stuff you need to produce that final demand comes in here. And here you have all the things you need to produce the inputs to the inputs to the inputs to the final demand. Okay, well, this game continues. If you want to do this out to infinity, you can look at all the inputs to 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 the inputs of your final demand. You're going to end up with terms like, well, A, as many times as you go through, times F will tell you the additional amount of final demand needed to fulfill that little incremental additional request caused by all the rest of the supply chain. Okay, well, the game here is to write down this matrix equation. This is the total amount of output you would need if you only needed to go 3 rounds deep in your supply chain. And you can rewrite this. The matrix A times the matrix A times the matrix A. We'll just get the shorthand notation of A cubed. That literally means take the matrix, multiply it by the same matrix, and the same matrix again 3 times. Okay, and fun fact that if you raise a matrix to the power of 0, just like in the scalar case, you get the 2 to the 0 is 1. Well, the matrix A to the 0 gives you back the identity matrix, which is just the vector F itself. Okay, so all I've done right here is done a nice little variable change to make the notation more compact. And then I'm going to rewrite that in a summation form, that the total output required for 3 levels of output in the supply chain is just summing a to the power I times F, where I ranges from 0 to k. So let k equal to 3 in this case. You get a to the 0 times F plus a to the 1 times F plus a to the 2 times F plus a to the 3 times F. In other words, this kth level of demand, or the kth level of total output required to satisfy this final demand, can be rewritten in this way. Okay, there's nothing special being done there. I've just pulled off the F term outside of the summation. What I'm allowed to do, though, is I can pull off one of these A's inside the summation to the outside. So instead of summing from I equals 0 to k, I can instead sum from I equals 0 to k minus 1. I'm allowed to do that because at the end of the day, I'm going to multiply all those terms by A out here as well. What does this actually say then? Well, it says before I just went from I equals 0 to k, AI, F. Now I've got a mathematically equivalent statement, which is A times a quantity which was raised to one lower power of F. But I need to be a little bit careful in the bookkeeping here, right? If you see now that I equals 0, if you do I equals 0 here, you have A to the 0, which is the identity matrix, times F. That's going to be multiplied by A. So I still need to, in order to be mathematically equivalent to this expression, there's a term F by itself that still needs picked up. So I pick up the F out here by itself, and then I'm just, for all the terms I equal to, originally in this expression, I equal 1 to k, I'm going to go from I equals 0 to k minus 1, and then multiply by A after the fact to get it mathematically equivalent. Why are you doing this? You're doing this to get a mathematically convenient expression in the final line, which is to recognize that this term right here, this I equals 0 to k minus 1 AI of F, is nothing more than the expression, look for it right up here, it's nothing more than the expression x of k minus 1. It's x of k minus 1. In other words, this term right here is x of k minus 1. Fine, call it that. Instead of having this really complicated expression, which kind of came out of thin air, if instead we call it what it truly is, which is x of k minus 1, then you get something that looks an awful lot like a dynamical system. It says the total amount of output needed in the kth round is nothing more than the final demand plus the additional output needed to fulfill the total output from the k minus 1th call. In other words, you're getting a final demand every time. You're going to need to make just a little bit more than the last time. You've got xk minus 1 total demand. Well, of course, that total demand requires a little bit of additional output to produce it, and that tells you how much you need for the kth round. This will continue. You can keep going to xk plus 1, xk plus 2, xk plus 3. What you'd like to see is eventually, as k gets larger and larger, that eventually the total output converges. In other words, every time you make an incremental additional request for resources, smaller and smaller additional resources, because it's the 4th or 5th or 6th or 7th time you've been on the phone call and you're trying to get everything to kind of equal out, that eventually those phone calls are for smaller and smaller and smaller orders. And that's in fact what is true. If you look at this dynamical system and you ask what its limit is, you can do that. And you'll find that the matrix A raised to the power I, when I goes from 0 to infinity, well, we can write it out. That is nothing more than I plus A squared plus A cubed plus blah, 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 right? That is mathematically equal to I minus A inverse. It's just a fact. I'm not deriving it. I'm not showing you how to do it. I'm just telling you that this summation does, in fact, have a limit, and that limit is I minus A inverse in a very special setting, which holds true for the EIO models. Well, where does it come from, and what is that special setting? Well, it's really hard generally to think about matrices, but you can always get some type of intuition by considering the scalar case, right? And if you look at the scalar case, instead of raising the matrix A to the power I, if you raise the coefficient, the scalar number A to the power of I, you can get something that looks like the following. there is an, a geometric series result that you probably covered and then since forgotten in your intro calculus classes, that if you sum the series alpha times a raised to the power I, where the coefficient goes from 0 to infinity, in the limit you will get that this series is equal to alpha over 1 minus a. Well, this expression here looks an awful lot like this one, with alpha being equal to 1, right? And a, instead of being a scalar, a is a matrix. Well, if you let alpha be 1, then you're left with something that looks a whole lot like 1 minus a raised to the power minus 1 is the limit of this expression. 1 minus a raised to the power minus 1. That's exactly what's happening here in this matrix world, where instead of dividing, we're actually computing an inverse. So it's a fact that if you take the limit of this matrix series under the very special case that now we're going to get technical for a half second, that the maximum eigenvalue of this matrix A is less than 1, which I'm telling you for a fact is true for the EIO models, then you get convergence. And the magnitude of the eigenvalues, whatever those things are, if you know what they are, great. If not, you don't need to worry too much about it. The magnitude of the eigenvalues being less than 1 is no different than the requirement you need for convergence of the geometric series, that the value A needs to have magnitude of less than 1 in order for convergence to occur here. So it's a long thought process to get through it, but what that basically says is if you look and you want to know what the convergence of this series x of k is when k goes to infinity, what is the limit of x of k as k goes to infinity, the main thing you need to know is what does this term right here converge to? Because this term right here, if it converges to something that we can calculate, we're in great shape, because that tells us, again, another way of saying it, is what happens to this dynamical system that's down here as we keep making more and more calls. As we've made the kth call, the k plus 1th call, all the way out to the infinitieth call, what is the final total demand we're going to need to produce, or the total output we're going to need to produce to get the final demand we have? Okay, well, it turns out then, as long as the A matrix has this special property, which on the EIO it does, then the infinitieth call, the total output after infinity steps of making requests in the supply chain, is nothing other than I minus A inverse. Okay, so what does it actually tell us? It tells us two things. I have just derived now two different ways to come to the exact same mathematical expression. You want to know what the total output is through an infinite round of iterations through the supply chain? Well, we built an expression that told us what each round k needs in terms of how much output you needed in the k minus 1th round, and we looked at what the limit of this thing does, or its long time behavior, or what happens when k goes to infinity, and we found that it's I minus A inverse. Well, another way of doing it, we never looked at the dynamical system, we just started with the fact that this is a system which is not a dynamical system. I just need to know the relationship of the total output and the final demand, and the total output is itself a function of the total output and the final demand. This function of the total output is the intermediate output, and we reasoned through that, and it turns out you get the exact same expression. So just two different ways to look at the mathematics that give you exactly equivalent mathematical expressions, and how you look at it is totally up to you. Okay, so let's look through a simplified example, and this comes out of the work of Chris Hendrickson and some of his collaborators, the pioneer of this approach. You'll see kind of like a pretty typical example from the civil and environmental engineering domain. You want to build a roadway. It's going to cost you $150,000, and you're going to end up with $46,000 worth of iron and steel in it, and you know that you're going to need $104,000 of concrete in it. You want to do a life cycle assessment. You really don't have an interest in going into the details of road construction. You don't want to build a process-based model to figure out how concrete is manufactured. You don't want to go into a process-based model and figure out how iron and steel is manufactured. You just want to, and by the way, you don't care about the specifics of how the steel or the concrete is made. You You just want to know on average what it's going to take. Well, we can use the EIO model. It's a simplified example here because we're rounding off a lot of details and we're getting rid of most of the sectors. But we can specify our final demand as this $150,000 roadway, which has nothing from most of the sectors, $46,000 from the iron and steel production sector here, and $104,000 of the concrete production. So this is our final demand vector, okay? Then what do? Well, the matrix A for the EIO model in this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sector economy has been computed for you already. So these are the AIJ values. Yeah, there's a little bit of rounding in here. Some of these zeros might be slightly larger than 0 out to 10 significant digits, but I put them in as 0 here just to keep it easy to present. So this is the A matrix that you either need to be given or need to be able to calculate from EIO data directly. In the EIO LCA tools, this stuff is like hard-coded into the source code. Okay, so we're given the A matrix. We know what our final demand is. We can calculate this matrix S, which is really the intensity matrix, via taking the A that was given to us and subtracting from the identity matrix that matrix A that we had on the previous slide, and then computing the inverse in Python. And this is what the matrix S gives us. What does it tell us? Well, as I indicated before, this right here, this column tells us the total amount of economic activity required for $1 of spending in the transportation sector. Let in the special case the F vector be 1, 0, 0, 0, 0, 0. Well, for the final demand, which you're going to stick right here, F times S, or said differently, S, the matrix S times the final demand vector S. Well, it's going to tell you the total output X needed. So for $1 of spending in the transportation sector as final demand, you need to produce $1.197 of total output from the transportation sector. In other words, it takes transportation to make transportation. If you want a final demand of transportation, there's an additional 1.97 units. Let me say it differently. The final demand is $1 of total transportation final demand, and of that you need to produce $1.197 worth of output from that sector. $1 goes to the final demand, and $0.197 goes somewhere else in the economy to help you produce that final demand. The $1 of final demand here says, again with the dollar final demand from the transportation sector, says you need nothing from aggregate mining. It will produce no economic activity in the iron and ores mining, nothing in the lime sector, but it will produce total output from the electricity sector of $0.017 and similarly $0.002 from the coal mining sector. And we can go down the list, right? But you can see right away that if you're going to do a $1 of final demand in the transportation sector, most of the money is going to go to, or most of the activity will occur in the transportation sector, with, it looks like, the next highest going in the electricity sector. Well, we can do the same thing for the aggregate mining. If instead of wanting $1 of the transportation sector, you wanted it from the aggregate mining sector, well, $1 of final demand in the aggregate mining sector requires slightly more than $1 of activity in the aggregate mining sector. $1 goes to the final demand, and $0.04 goes to other sectors of the economy as intermediate output. Some of it goes to the transportation sector, some goes to electricity, some goes to coal mining, and so on. You can see that $1 of spending in the transportation sector generates more than $1, quite a bit more than $1 of activity from the transportation sector, not quite as much activity for the same dollar spent in the aggregate mining sector. And if you spend $1 in the iron and ores mining sector, it actually generates even less total economic activity in the iron and ores mining sector. In other words, these sectors basically don't have that much other demand inside the economy. Buying $1 of iron and ores doesn't really do a whole lot for the iron and ore mining sector. It doesn't add that much more additional economic activity. Iron and ores mining doesn't really depend itself that much on iron and ore mining. That's another way to think through this stuff. Well, there's other fun things you can do with this vector or this matrix S, right? So one thing you could do is you could sum down this column. In other words, add 1.197 to 0 to 0 to 0 to 0.017 to 0.002 and so on, right? What does summing down do? Well, that tells you, again, for $1 of spending in the transportation sector, the total amount spent in the transportation sector, total amount spent in the electricity sector, total amount in the coal sector, total amount in the additive sector. Summing this thing tells you the total amount of spending in the economy for $1 of final demand in the transportation sector. In other words, if you sum this down, it tells you how active that dollar will be in creating additional economic activity for you. If this sum in the extreme case is a really, really small number, like barely larger than 1, it basically says $1 of final demand, it doesn't really do that much to create additional spending in the economy. If this number is really large, suppose this number comes out to something like 2, then what it says is for $1 of spending in the final demand of the transportation sector, you would have $2 of spending everywhere in the economy. It generates a total of $2 of spending everywhere else in the economy. That's actually a pretty powerful thing, right? It basically tells you that the larger the column sum of the sector is, it tells you the more sort of impactful in terms of the economy that dollar of final demand spending is in generating economic activity. Okay, well, if you look at the column sum and it's informative, you can also ask, what does the row sum tell you? What does the row sum tell you? Well, the row sum tells you if you spent $1 in every sector. If you spend $1 in every sector, let F, the vector F, the final demand, be 1, 1, 1, 1, 1, 1, 1. Well, then the equation would be X equals S times the final demand vector, which is a bunch of 1s. It will tell you the total output X from $1 of spending in each of those sectors. Okay. Do you end up seeing a lot of activity in the transportation sector? Or do you see most of that activity go to the iron and ores mining sector? The iron and ores mining sector, you can see there's a lot of zeros here. 0, 0, 1, 0, 0, 0. I mean, these are all relatively small numbers compared to if you look just kind of 1 up or 2 up to the transportation sector, that the row sum here is smaller compared to the row sum here. It means the transportation sector has more other sectors depend on the transportation sector. In other words, the transportation sector will be doing economic activity in support of final demand across these sectors compared to the iron and ores mining sector. That tells you something about how important the transportation sector is relative to all of the other sectors of the economy compared to the iron and ores mining sector. The transportation sector turns out to be just more important. Okay, another thing that you can do is you can look at the relative magnitude of Sij and Aij. The Sijs are all larger than the Aijs, and some are quite significantly larger. Well, remember that Sij has the interpretation; it's the total amount of output required for a final demand of $1 from sector J, where Aij has a different interpretation. It's the total amount of input required from sector I to produce $1 of intermediate output from sector J. So it's the difference between the total output and the intermediate output. In other words, so you can look at the multipliers here. Some of these things are basically telling you that that you get a lot more total output from a sector compared to intermediate output, where others are less so. So, for example, iron and ores mining, there's a lot of total output from that sector relative to the amount of intermediate output required for that sector. And it's not a coincidence that all the numbers are greater than 1. Occasionally you'll see things like infinity. That's because if Aij happens to be a 0, then obviously that term will go to infinity. Okay, so that's an aside on things that you can do with the S matrix compared to the A matrix. Actually, continuing to the actual calculation, if I specify the final demand for a $150,000 roadway, I plug it into F, I compute I minus A inverse, I take that matrix and multiply it by our final demand. That gives me the total output required from all the sectors. So I plug in my F vector into my I minus A inverse matrix or my S matrix, and I get the total output, $12,000, $12,000, $1,000, less than $1,000, and so on. Okay, and so what is fun to do here? This is the total output required from all of those sectors to produce the $150,000 roadway. If we sum down this vector x that we calculated, we can see that we'll get a total of like $225,000 worth of economic activity. In other words, building that $150,000 roadway induced $225,000 of total economic flow in the economy. Where like economic engineering comes into play is to say that, well, rather than building a $150,000 roadway, what else could I have built that would have led to, could I have spent my $150,000 in a different way? Could I have spent my $150,000 in a different way by spreading it across these different elements in the final demand, or bundling it into only one of them? And where would it be the most impactful? If a $150,000 road generated $225,000 worth of economic activity, maybe if I had just invested it all in the transportation sector, maybe I would have got even more economic activity. Or if I invested it in the iron and ores mining sector, maybe I would have gotten less economic activity. The way to roughly see that would be to go back to your vector or your matrix S here and look at which one of these columns of S has the largest column sum, because the column sum is telling you for $1 of investment which one's going to produce the largest total output. Well, if per dollar it produces the largest total output, then for $150,000 it will just produce $150,000 times that amount. So these column sums again tell you sort of the most intelligent way to spend your money if you've got a fixed budget and your goal is to maximize that number rather than just find the total economic activity. Okay, so that's the EIO model. There's nothing actually special about it in terms of life cycle assessment until we're able to compute coefficients that tell us what dollars of spending in the sector do for emissions. So I want to know ultimately an emissions vector B, and if I have call it M interventions, I know I have N sectors of the economy. That means I'm going to need M times N coefficients that convert dollars of spending or in total output from a sector 1 through N into emissions categories 1 through M. So for example, each element Cij is going to have units of whatever the intervention is, call it tons of CO2. Tons of CO2 for $1 of output in sector J, right? Where I could be tons of CO2, I could be tons of methane, CO2 equivalents, whatever you like, right? But it converts into those inventories per dollar of spending in sector J. Well, just like we did for the process-based LCA, we can stack all that stuff in a matrix, and that does us nothing more than takes our total output, I minus A inverse F for a specific amount of spending in sector F, and that will allow us to calculate the interventions vector B. Well, in the same way that we did these tricks in the past where instead of you specify the final demand, I go ahead and take I minus A and then I invert it, and then I multiply whatever I've got left by this matrix C. I can instead multiply C times I minus A inverse, and that will give me the interventions intensity. Per dollar of spending in the final demand F, what will the actual environmental interventions look like? So we can directly calculate which processes per dollar of spending are worst for the environment. And the same tricks we did for the matrix S we'll do for this new matrix, which is C times S or C times I minus A inverse. Okay, so these are the same kind of tricks we've been playing now on several occasions. If I give you one of the rows of C, and let's suppose it's for one of the hazardous waste, and I tell you for the final demand X we just calculated when we looked at the $150,000 roadway, if I've got the coefficients that tell me how much hazardous waste I get per dollar spending in each of those sectors, here's the coefficient in hazardous waste for $1,000 of output in the second sector, and here it is for the third sector, and so on. Well, I just need to take all, this coefficient times this first total amount of spending in that sector plus this coefficient, which tells me, again, hazardous waste materials per dollar or per $1,000 of the second sector, and so on. Do the row times the column, and you'll end up with something like 3,000 tons of hazardous waste material as a response of building this $150,000 roadway that generated $225,000 worth of economic activity. Okay, so what's the point of doing the process-based LCA compared to the EIO LCA? Well, there's advantages of both, right? If you're a company and you care about specific processes and you want to do detailed comparisons, like whether a Mac is better than a PC or vice versa, you can't just throw out $1,000 a computer compared to $1,000 worth of computer. You need to know details about the processes used to make those computers to assess whether they're better or worse for each other. On the other hand, you have to get into really detailed modeling to get to that level of specificity, and then you run into all kinds of challenges with data availability. The EIO models don't require any of that specificity. They literally average out the nuances of how each company in the sector is working efficiently or inefficiently, dirty or clean, and gives you the sort of aggregate efficiency and the aggregate emissions that are produced per dollar of output for that sector. Well, the process-based LCA and the EIO LCA have different weaknesses too, right? The processed one is expensive, it's time-consuming. If you have to go out and do this in private industry, you've got to buy a multi-$1,000 database. The EIO LCA, it's all made with open source data, so it's free. That's a huge advantage when you're trying to make your LCA consulting company profitable in the first couple years. But the problem generally is the fact that everything is based on money. So we went through this example between the differences of consumer and producer prices. Something's expensive or something's cheap. Obviously, you're going to get different emissions associated with how much markup there is if you're not careful. I mentioned the fact that the models are quite old. That's just an artifact of the fact that it's a free tool and it uses economic data that is slow to produce. And it's actually really difficult to apply in some parts of the world. If you're a country that is highly dependent on inputs and outputs that come from sectors outside of your country, like basically you do a lot of importing and a lot of exporting, then your internal economic model depends entirely on how things work in other countries' economies, in which case you don't have any data on it. It's really hard for you to build a good model. In other words, if you're importing all of your food and all of your steel and all of your coal and all of your electronics and everything else, then it doesn't do you any good to look at your economic input-output model and look at how much emissions were produced in your country in the process of producing a token amount of steel or a token amount of food or a token amount of computers, because all the emissions happened in somebody else's economy. You would need to go model their economy and how clean or how dirty they produce things in order to get good estimates of the total environmental impact of your process. So if you've got an open economy with a lot of inputs and a lot of imports and exports, it's just not going to help you to build an EIO model. There's a whole bunch of techniques that have gone beyond the two main LCA approaches I've shown you, the economic input-output model and the process-based LCA. There are hybrid approaches that kind of combine information from the two approaches. A lot of these you can read about online. Chris Hendrickson has a book out on exactly these topics that kind of link together sort of the best processes from the process-based and the EIO LCA. So I'm going to wrap up the discussion of the EIO models here, and then we'll switch over on the next lecture to just kind of walk through some of the pieces that you can expect to see on your project. Thanks.